Okay, well, my name is Udayan. I am an alum from the class of 2011. I'll just start by saying a little bit about me and the one piece of advice I maybe have, and then we'll get to the fun stuff. So I graduated TAMS 2011. I went to the University of Chicago for undergrad, and I ended up studying math and economics. After I graduated, I wasn't really sure what I wanted to do for a little while. I thought I wanted to be a math professor, but after doing some math research, I reevaluated a little bit. I worked for 2 years in the private sector at a hedge fund. And then afterwards, I went to Northwestern. So I'm currently at Northwestern. I'm doing a PhD in economics, and I'm having a great time. I'm absolutely loving it. And yeah, that's basically what I have to say about myself. So if you have any questions about, grad school or working in the private sector or stuff like that, I will be more than happy to answer. I guess the one piece of advice, or I guess you can loosely call it advice, that I would give is that you probably don't value experimentation highly enough, in the sense that, if you go to school and you think you really want to study math, like I did, it's worth trying some other stuff out. Like I worked in an epidemiology lab when I was at TAMS, and I did a little bit of computational neuroscience when I was at UChicago. It turned out I didn't love the latter, but I learned some things, and more importantly, I learned about myself. So I guess the one big piece of advice I have to offer is experiment a lot. Okay, so I guess on that note, I will share my little presentation, which is about matching. It's the first or second topic that got me really interested in economics, along with game theory. And I think it's at a great intersection of math and economics and computer science, and has kind of a very nice application and appeal. So I'm going to attempt to share my screen here, and let's see how well this works. Okay, so can everybody see this presentation right now? I see some nods. Okay, great. So this is going to be a presentation on matching. It's going to be pretty basic. Hopefully you learn some things. Maybe it's interesting. And if you are interested in medicine and at some point might be doing doing a residency somewhere, this presentation will also be a little relevant to you. So at any point, if you have a question, you should definitely cut in and ask. There'll be a few points where I will stop and wait until somebody asks me a question, just so I don't feel like I'm talking to a wall. But yeah, so those are the terms of engagement. Just jump in whenever you would like. Okay, so it's going to be about matching, and the first thing you probably want to know is what is matching. All right, so here are some examples. The first one is kind of the quintessential example of matching that you will almost always see, which is the National Residency Matching Program. Right? Matching is in the name, probably a good example. If you want to be a doctor at some point after you go through med school, you apply to do your residency. And by apply, I really mean you submit where you would like to go to residency to the NRMP, and they collect that data as well as data from all the different hospitals about who they want to admit. Right? So maybe you're really interested in, I'm trying to think of a good example now. Maybe you're really interested in doing internal medicine, right? And you know that there's a couple of good schools that you really want to go to, and you list whichever ones are your top choices. And the schools say the same. They say, oh man, Udayan, he was a really bad student. I don't want him. But maybe Manisha was a great student. We'll rank Manisha higher. Right, something like that. And then the NRMP collects all this data, and then they do some magic, and then they present all of the matches. They say, okay, Udayan, nobody wanted you, too bad. Manisha, you'll go to Harvard, whatever, something like that. Okay, another example is college admissions. Maybe for the TAMS students that are watching, this is a little too close to home right now. This is a good example of a decentralized matching process, right? You apply to different schools, they accept or reject you. At the end of the day, you figure out where you want to go. And it's decentralized in the sense that even though there is a common app, you're not submitting all your information to a centralized decision maker. You're interacting with each school individually. And at no point, or probably at no point, do all the schools get in the same room together and decide who's going where. Another example is organ donations. Right, there's people who have organs to donate, and there's people who need organs. And deciding who gets which organs and the way that the wait list works is another matching problem. And this one is interesting because it's dynamic, right? Over time, there's more people who need organs, and over time, there's more organs that become available. So you're doing matching, but it's evolving over time. And then the last example is just like housing markets, right? Where maybe you're just trying to decide where you want to live, and there's a bunch of people looking for houses. And the question is, how do people end up in different houses? And a lot of markets kind of work like this. And in housing markets, there's a feature that is, maybe not as clear in the other ones, but that's just payments, right? Maybe if I'm willing to pay more to live in a house, I should get to go to that house, or I should be allocated that house. Okay, so here's some examples very broadly of matching. It's a super broad subject. But now I'm going to stop and I'm going to ask if anybody else can think of any examples of matching in their life or perhaps at TAMS. And if you have one, you should just go for it. Okay, and I'll give you a little hint right now. When you applied to TAMS, or when you were at TAMS, one of the first things you had to do was figure out who to live with, right? So choosing roommates is also a matching problem. Right? You can imagine TAMS has 100 people that they need to match. Miranda was going to say that, and that's exactly a great example, right? They have a bunch of people that they need to put into rooms together, and then how do you do that? Right, the roommate problem is a little interesting because there's not a clear delineation. There's not like two sides, right? On the residency example, there's doctors, there's hospitals, right? But in a roommate problem, you have maybe 100 people, you can split them into pairs kind of however you want. Right? So there's a lot more ways to make matches, and that makes the problem more difficult. But these are just some examples, and there's tons more. So let's see. So what are the common features of these kinds of problems? With the exception of the roommate problem, there's at least two groups that are going to be paired, right? They're people or institutions or objects like houses, right? And at least one group has preferences over their match, right? I care about where I want to go to school, and presumably schools care about whether they admit me or someone else. So for this little talk, I wanted to focus mainly on two-sided matching, right? Which is where both groups have preferences over their partners, right? So I'm not thinking about like housing allocations. I want to really fix the specific idea or the specific example of doctors and hospitals. So everything that I'm going to talk about from here on out, I'm going to be using doctors and hospitals as my two groups that need to be matched. Okay, are there any questions so far? Okay, great. So let's get into it. So this is, what a rough a very basic economic model might look like. Like, what are the ingredients we want to think about for this kind of problem? And we like calling these primitives, right? They're things that we just take for granted, and we're not saying necessarily where they come from or whether they're right or wrong. They exist. So there's going to be N doctors and M hospitals, right? So N and M are two different numbers. So maybe you've got 100 doctors and 10 hospitals. And we're going to make a great simplifying assumption, which is that each hospital is looking for at most one doctor. Now, this is obviously not realistic. this is just going to be for the sake of this little lecture. But I'm just going to say that things get very complicated very quickly when hospitals have more complex constraints or preferences. Right? Something that would be very complicated, for example, is if doctors have kind of different quotas that they need to fill, right? Like they can only have one internal medicine resident and one pediatric resident. Then all of a sudden, when you're asking whether hospital prefers this group of applicants or that group of applicants, it becomes trickier. It can be dealt with, but it's going to make our lives way simpler if we just assume that each hospital is looking for one doctor. Okay, and then the other thing we're taking as given is preferences. Again, we're not judging or saying whether they're right or wrong, but we can't influence them. They just exist. So each doctor, we're going to say, has a strict preference ranking over hospitals, and they kind of omit unacceptable ones. So this is an example, right? A doctor might prefer H1, which is hospital 1, to H2, which is hospital 2. Maybe they prefer like Harvard to Hopkins, and they would rather go to Harvard over Hopkins over nothing, right? In the sense that the next best thing for them is to just not be matched, and they would rather not be a resident at all, rather than go to H3, which, let me think of a good H name now, Houston, right? Maybe this is their preference. They want to go to Harvard first, then Johns Hopkins, and they would rather just not be a doctor than go to Houston. And similarly, we're going to assume that each hospital has a strict preference ranking over the doctors that they admit. Right, and this is kind of the fundamental or the key ingredients that we're going to need. Does this make sense to those who are watching at the moment? I generally see some nods. Okay, great. So these are the ingredients to play with. And what is our job, right? We want to take the role of a central planner, right? This like mythical econ figure that you'll probably hear economists talk about to no end. And our job is the following, right? We have doctors' preferences taken as given. Just doctors tell us where they want to go and what the ranking is. And we have hospital preferences also as given. They just say, this is the order of applicants we want to admit. Okay, and those two things are coming to us. And then we need to do some magic, right? Our job is going to be to fill out this black box that currently says magic. And then at the end of the day, we're going to have an assignment, right? At the end of the day, we're going to say, Udayan, you go to Houston. Too bad, I know it was your last choice, but that's where you go. And then Manisha goes to Harvard, and then poor Dr. 3, you know what? You don't get to go anywhere. No hospital wanted you. And this is the assignment that we've come up with. Right, so this is kind of our job, is to say, how do we transform the preferences of the doctors and the hospitals into an assignment? Okay, and then the very first question we should ask is, how do we know if we've made a good assignment? How do we know whether pairing people to pairing doctors to hospitals in this way is good in some sense, right? And so the hard part is actually defining what the word good means. What does it mean to make a good assignment or not? So the kind of conceptual task is, how do we respect people's preferences in the right way or in a good way? Okay, so here's a little example. You can see very clearly that art is nowhere in my list of skills, so prepare for some very janky animations for the rest of the presentation. This is the way I'm going to illustrate it. So doctors are going to be these green circles, and hospitals are going to be these blue circles. Okay, so we have 2 doctors and 2 hospitals. And I've written everybody's preferences next to them. So this first doctor would rather go to hospital 1 than hospital 2. This doctor would rather go to hospital 2 than hospital 1. The first hospital wants doctor 1 over doctor 2. And the second hospital wants doctor 2 over doctor 1. Right, so these are all the ingredients that I said were just given. Okay, so how do we respect these preferences? Well, let's start with saying what do we think doesn't respect these preferences? So what is something bad that we can do? So here I'm going to give you what I'm going to say is a kind of obviously bad assignment. So what I'm going to do is I'm going to say, all right, I'm going to match doctor 1 to hospital 2. And I'm going to match doctor 2 to hospital 1. And my claim is that this is kind of just an obviously bad assignment. So What I would like is for somebody to maybe tell me why they think that this is a bad assignment, given the preferences of the doctors and the hospitals that I've just told you. If anybody has an idea of why this is maybe not a good way to do things, should jump in and say something.
Both doctors are unhappy given this.
Yeah, exactly, right? Both doctors are unhappy given this. And beyond that, actually both hospitals are also unhappy, right? So this doctor, he really wants to go to hospital 1. And hospital 1 really likes doctor 1. So really we should be matching doctor 1 to hospital 1, right? That makes them both have their first choice. We should be matching hospital 2 to doctor 2, right? Then they both also have their first choice, right? And that seems kind of clearly better than whatever we've come up with here. Okay, so this is, yeah, and everybody, I didn't see the chat earlier. Thank you to all those who were speaking. Yeah, it's totally a lose-lose situation, right? Just nobody is happy about what we've done here, and this would be a big no-no. So that's something that's clearly bad. Now what I'm gonna do is I'm gonna take this same set of doctors and hospitals. I'm gonna change hospital 1's preferences. So now hospital 1 also likes doctor 2 best, followed by doctor 1. Okay, so both hospitals actually like doctor 2 over doctor 1. Doctor 1 likes hospital 1, doctor 2 likes hospital 2. And now I'm going to give you an example of something that's maybe not obvious, but I'm going to say is still a bad assignment. Okay, and here's the proposed assignment. It's actually the same one as before. I'm going to match doctor 1 to hospital 2. I'm going to match doctor 2 to hospital 1. And I claim that this is actually still bad. It's not as obvious as the last one where, you know, everybody, we wronged everybody, but this is still not so great. So I want to give people just a second to think about why maybe this is not a good assignment. And if anybody has an idea, you should jump in either to voice or to the chat. Okay, so what I'm seeing is people saying things like only one preference has been met. And that's right, but let's be a little more specific. And again, I said this is not obvious and it's not easy to see why this is bad, but here's one reason why this is bad. Both hospitals really want doctor 2, right? They both think that doctor 2 is the best. But somehow doctor 2 has not ended up at her top choice, right? Doctor 2 has ended up at hospital 1. Both of these people really want doctor 2. Doctor 2 has ended up at hospital 1, and that doesn't seem very good. Another way to say it is, imagine that we set up this assignment, and then somehow, you know, doctor 2 sends an email to hospital 2 and says, oh, I'm really sorry, I wish I could have come, it would have been great. And then hospital 2 responds and says, oh, wow, actually, that'd be great. Do you want to come? And doctor 2 would say, yes, that's way better than what I wanted to do or where I've been assigned, right? So the idea is, if doctor 2 and hospital 2 met in the wild somewhere, they would both really say, you know what, this assignment that you've given us is terrible. We're going to join with each other rather than what the central planner has said that we should do. Right? And another way to say it is we are respecting more preferences in this way, in the sense that, again, I'll say it one more time. If doctor 2 and hospital 2 met up, they would rather be with each other than with their respective counterparties. And there's a great thing I just saw in chat, which says it depends on whose preferences are prioritized, and we're going to get back to that. It's a very great point. Okay, so this is the kind of criterion we're going to use. And so now we're going to get a little more formal. We're going to use the stability criterion. And we think that we, being economists, think that this is maybe kind of a minimum threshold of what we want for an assignment to be good. Okay, so we're going to say that an assignment is stable, so definition, if there does not exist a pair of doctor and hospital such that they both prefer each other to the counterparties that we've assigned them, right? And if we can find such a pair, we're going to call that a blocking pair. Okay, so in the example that we just gave, Let's see if these animations stay or go. In the example we just gave, Doctor 2 and Hospital 2 are a blocking pair, where they both prefer each other to the counterparty that we've assigned them. And we're going to say, what we really don't want to do, we really don't want to create an assignment where there is a blocking pair. Or equivalently, at the very minimum, we want to create an assignment that is stable. So this is like the threshold we're going to use. And there's ways that you can strengthen this idea. But this is maybe the first bar that we want to cross. And the reason we want stability is it means that doctors and hospitals have no incentive to leave the mechanism that we've put together. Right? It would be really bad if all of a sudden we were doing this thing and the doctors and hospitals found out that if they just talked to each other without the central planner, that they could be doing better. Okay, but this now raises many questions, right, related to stability. The very first question is, do stable matches always exist? Like, we want a match to be stable. We want a pairing to be stable. Can we even guarantee that that's possible? Are there weird preferences of doctors and hospitals where we can't even get stability, right? Another question is, are there many stable matches? It's possible that we have tons of different ones, and if there are some better than others? You know, it's hard to say. Oops. Another question is, how do we implement them, right? Suppose somebody came along and told you a stable match always exists. How do you find it, right? This could be a very complicated problem if you've got hundreds of doctors and hundreds of hospitals. How would you even put them together in a stable way? And the last question, which is a little bit in the background, is, do people have an incentive to try to cheat this mechanism that we're going to implement? And we'll get back to that at the very end, where it'll be a little more specific, but it'd be really bad if we tried to say something like, we're going to create this great mechanism. You just tell me where you want to go, and we'll do the best we can. And then people found out that by lying about where you wanted to go, you could be better off. You could cheat the mechanism. That'd be very bad, because then we wouldn't even know what people's true preferences were. So these are the kinds of questions we want to ask. And we're going to answer many of them at once using an algorithm. Right? So remember how I said at the beginning, this is a nice topic in between math and economics and computer science. We're going to give you an algorithm that is going to first show that there always is a stable match. Second, give you the best stable match from the perspective of the doctors. And it's an algorithm, so it'll give you a way to implement that stable match. So this is actually the foundation for the algorithm that the National Residency Matching Program uses in order to pair residents to hospitals. Okay, and it's called the Deferred Acceptance Algorithm. And I put in parentheses, doctors propose. So I'm going to describe to you in a second how this algorithm works. But before I get into it, are there any questions so far about what we're doing or what our goal is? Okay, great. So here's the algorithm. The algorithm runs in steps, like many algorithms do. Okay, and each step is actually going to be broken up into two parts. So we have step 1A, and then we're going to have a step 1B. So step 1A is the following. Right? We've been given everybody's preferences, and now we're going to simulate this situation. So first, all the doctors are going to apply to their top choice hospitals. Remember, we said doctors have a strict preference ordering. In other words, they prefer to hospital 1, to hospital 2, to hospital 3. We're going to say, each doctor, we start out, everybody apply to your top choice hospitals. And this is something that we're simulating. Okay, now in step 1B, all of these doctors have applied. Some hospitals maybe have multiple applicants. Some hospitals maybe have none. Every hospital waitlists the top applicant that they got, and they reject the rest of them. Right? So if you had only one applicant, well, you're probably going to waitlist that one person unless they're unacceptable. And that's your only choice. If you have multiple applicants, then you're going to only waitlist one of them, and you're going to reject everybody else. Right? You're going to waitlist your favorite applicant. So that's what happens in step 1A, which is the proposal phase, and step 1B, which is the waitlist phase. Okay, and then we're just going to repeat this. We're going to repeat it many, many times. So in step K, right, so what would be K is 17. On step 17, again, all doctors who are not waitlisted, we're going to apply to their highest ranked hospital that has not rejected them already. So maybe you've applied, we've been simulating this thing and you've applied and a couple of hospitals have rejected you and you are currently not waitlisted. You apply to your top ranked hospital that's left. And by left, I mean the top ranked hospital that have not applied to already. And then hospitals do the same thing. They waitlist their top choice applicant and they reject the rest. And it's going to continue. We're going to iterate. We're going to keep going. We're going to keep going until eventually we're going to stop. And we're going to stop when either everyone is on a wait list at exactly one school or people have been rejected by all the hospitals that they've applied to. We're going to run this algorithm until it terminates. So I'm going to give you an illustration of what this algorithm is, and it's, I think, very intuitive once you see this janky little animation. Okay, so here's the illustration. We have 4 doctors. Ooh, this little presentation note is covering up one of them for me. I don't know, can you all see this 4th doctor down here, or is there something covering it on the screen? Okay. Okay. So I'm going to try to not move my mouse too much, but I'm going to have to rearrange some things on my screen. Okay. So we have 4 doctors on the left, 4 hospitals on the right. Hopefully that's still left and right. And for each one of them, I've listed their preferences out. All right, and you know, very tedious, and there's a lot of information on the screen right now. But luckily, we only have to look at things one step at a time. So we're going to run the deferred acceptance algorithm as I just described it to you. So the first step is that doctors are going to apply to their top choice hospital. So Dr. 1, we look at Dr. 1's preferences, which are right here. We see that Dr. 1 wants to go to hospital 1 the most. So Dr. 1 is going to apply to hospital 1. Dr. 2 also wants to go to hospital 1 the most. So they're also going to apply to hospital 1. Dr. 3 is going to apply to hospital 2. And Dr. 4 is going to apply to hospital 4. Right? These are the proposals, or the applications, where every doctor applies to their top choice hospital. Okay, so here's what it looks like after they all propose. Boom, there it is. So you see hospital 1 has 2 applicants, where both Dr. 1 and 2 thought hospital 1 was the best. This hospital only has 1 applicant. This hospital has none. And hospital 4 also has 1 applicant. So that was part A, right? The proposal phase. Now we do the waitlist phase. So every hospital looks at their collection of applicants and says, who do I like the best amongst this group of applicants? They waitlist that person, and then they reject the rest. Right? So for these 3 hospitals at the bottom, it's very simple. This hospital doesn't have a choice. There's only 1 person. This hospital doesn't have any applicants. That's a little sad. Hospital 2 also only has 1 applicant. So these 2 doctors are going to be waitlisted. And hospital 1 has a choice. They say, okay, we have Dr. 1 and Dr. 2 that have applied. Who do I like best? We look over at these preferences. We see that this hospital prefers Dr. 1 to Dr. 2. So what they're going to say is, all right, Dr. 1, you're waitlisted. And Dr. 2, I'm so sorry, you've been rejected. So Dr. 2 hops back over to this left-hand side. Oops. And you can't see it too well because I used the letter H, but now I'm going to put a little dash through the letter H. This is indicating that this doctor applied to hospital 1 but got rejected. Okay, so that was step 1, right? Doctors applied, then hospitals waitlisted their favorite applicant and rejected the rest. And now we just get to repeat the whole thing. We're just going to keep going. So we look at everybody who's unmatched. So at this point is just Dr. 2. And we say, Dr. 2, apply to your favorite hospital that has not rejected you already. So hospital 1 has rejected them. Hospital 4 has not. So this doctor goes and applies to hospital 4 now. So this is the second proposal phase. Now hospital 4 does the same thing that hospital 1 had to do last time, where they look at their 2 applicants and decide who do they like best. looking at the preferences, this hospital prefers Dr. 2 to Dr. 4. So they're going to wait list Dr. 2, and they're going to sadly reject Dr. 4. So Dr. 4 goes back to the left-hand side after being rejected. And now we just keep going. That's great. We're just going to keep running the simulation. And now Dr. 4 is going to apply to the hospital that they like the best that has not rejected them, which is hospital 2. So Dr. 4 applies to hospital 2. Hospital 2 says, between Dr. 3 and Dr. 4, I prefer the latter. They're going to keep Dr. 4, and Dr. 3 sadly gets unmatched. They were on that wait list for a long time. They're probably pretty hopeful, but things have not gone their way. Now, lastly, Dr. 3 says, okay, time for me to apply. I'm going to apply to hospital 3. So now Dr. 3 applies to hospital 3, and all the hospitals are full, right? Every hospital has exactly one applicant left that they are okay with keeping, and they have nobody left to reject. So now we say we're done. Okay, we've done the whole iteration over and over again, and there's nobody left that is unmatched, or rather, everybody is waitlisted somewhere, and now we're going to lock in those waitlists. So this is the final allocation. Dr. 1 and hospital 1 are paired, Dr. 4, hospital 2 are paired, etc. Right, and so this is just the way the algorithm runs. There's a proposal phase, and there's a waitlist phase. We go back and forth until eventually we're locked in, or rather, eventually the algorithm will terminate. Now we should stop for a second and just eyeball, who do we think did well here? Right? Do we think that the doctors did well here? Do we think that the hospitals did well here? Well, let's look at the doctors. Dr. 1 got their first choice. It's pretty good. Dr. 4 down here got their second choice. Dr. 3, who is right here, got their second choice. Dr. 2 also got their second choice. That seems actually quite good. Right? The doctors generally got their first or second choice. What about the hospitals? Well, this hospital got Dr. 1, which was their third choice. Not great. This hospital got Dr. 4, which was their second choice. That's not bad. Hospital 3 got Dr. 3, which was actually their very last choice. They're probably pretty unhappy about this. And if you remember, they were stuck with no applicants for a long time. So maybe it's not surprising. And then Hospital 4 got Dr. 2, which is also their second choice. So just eyeballing it, it feels like the doctors did pretty well here, and the hospitals maybe did a bit less well here. But this is the way the algorithm works, and now we can just talk about some of the results, right? Let's remember the kind of questions we asked earlier. Do stable matchings always exist? Are there multiple of them? How do we get to them? Are some better than others? Okay, so this is basically like the last slide that I have, and here's some results. The first is the deferred acceptance algorithm always ends, and it ends with a stable assignment. It doesn't matter how many doctors or how many hospitals you have, this algorithm is guaranteed to stop. You're never going to get into some kind of weird cycle. And when it stops, you have found a stable assignment. So this is great news, right? We've both shown that a stable assignment always exists, and we've shown you how to make one. What's even better news is that this algorithm, with the doctors proposing, is doctors optimal. And what that means is, out of any possible stable matching, of which there are actually multiple, this one does the best for every single doctor. There is not a stable matching where any doctor does better than what we've just assigned them. So in some sense, doctors are as happy as can be using this algorithm. Hospitals, just based on the rough thing that we looked at last time, could probably do better. And in particular, if you ran the deferred acceptance algorithm where the hospitals proposed, that would generate the hospital optimal matching. Okay, so this algorithm gives you the best possible matching for the doctors. It ends in a stable assignment. And the very last thing I said here is that the deferred acceptance algorithm, when doctors propose, is strategy proof for the doctors. Now you probably are thinking, wait, where did strategies come from? I haven't heard anything about strategies. And it relates to the very last question that we asked earlier, which is there an incentive to cheat the mechanism, right? Now we know as doctors exactly how this mechanism is going to be run. is it possible that it benefits you to misreport your preferences, right? Maybe you're trying to act strategically and say something like, oh, I really want to go to Harvard, but maybe there's a lot of competition, so maybe I'll be better off if I put Harvard second and put Johns Hopkins first, something like that. That's naturally something that would go through your mind. And what this result says is that actually you don't want to do that. No matter what anybody else's preferences are, as a doctor, your best thing to do is to truthfully report your preferences. Right? So this is also great news, right? It means that the doctors have no incentive to lie about where they want to go. They just want to truthfully report their preferences. One small note is I've said that this algorithm is strategy proof for doctors. It is actually not strategy proof for hospitals. In fact, there's another theorem that I didn't present, but it is impossible to have an algorithm that is both strategy proof for doctors and for hospitals. It's impossible to get both. Right? So you either get that the doctors always report truthfully or the hospitals always report truthfully, but you can't guarantee the both of them, which another way of saying that is it is possible that a hospital would want to lie, but I would say that you shouldn't be worried about this in the sense that it would require the hospital to know all the preferences of all the doctors and all the other hospitals to figure out what a good lie is. And that's probably way too much information for any hospital to reasonably think about. Okay, but these are the basic results, right? We set up this problem, a matching problem. We decided what makes a good matching in some criterion. And then we found an algorithm to do it. And we show that the algorithm is good and that it's doctors optimal and strategy proof, where doctors want to report their preferences truthfully. Right? And so everything I've told you right now is based on a paper from the 1960s, which is crazy how old this is, but it's a paper by Gayle and Shapley that describes this whole algorithm using a different example, but the fundamental idea is exactly the same. Right? And since then, there have been many extensions, which are kind of on the right-hand side of the screen. So a very practical one is, as a doctor, perhaps you have a partner, right? Like a husband or wife or whatever, and you care not only about where you end up, but where your partner ends up. That's not something that we allowed for in the preferences that we originally had. Right? It was either, rather, each doctor only cared about where they ended up. So there are some extensions to deal with this, right? And some of the other extensions that I've mentioned before are on a dynamic allocation, right? Something maybe like a rolling admissions, or this, what the econ world loves calling it a kidney market or a kidney exchange. And the last thing that we didn't think about at all in this model is payments, which economists like to call transfers, right? Nowhere did we say anything like, I would rather go to Harvard than to Johns Hopkins, but if Johns Hopkins pays me a lot of money, you could change my mind, right? There was never any kind of opportunity for the two hospitals to compete over how much they pay or anything like that, right? So these are all different kinds of extensions. Many of them have been done in the literature, but there are ways to extend this basic model. And kind of what I wanted to emphasize is that, you know, we made a ton of simplifying assumptions here, right? Which economists love to do, right? We assume that each hospital only wants one doctor and all this kinds of stuff. But what I want to emphasize is that there are ways to expand the model and expand the algorithm to incorporate all kinds of different things. And, you know, natural questions are, how do we redefine stability now? Is stability still guaranteed? Do we want something other than stability? And there's, you know, a billion papers that if you're interested in, I would be happy to send you links or presentations from other professors about some of those other results. So that's basically all I have in terms of this mini lecture. And now I'm going to open it up to questions. And I see one in the chat already, which is great. And it's from Dave that says, would it be beneficial for hospitals to report all their preferences to the other hospitals to game the system? Right, that's a great question. Remember how I said earlier, it is possible that a hospital would like to game the system. Using the deferred acceptance algorithm, where doctors propose, it is impossible that a doctor would like to game the system, but it's possible that a hospital might. And in particular, they would need to know a lot about other hospitals' preferences. And the question is there any reason why, as a hospital, I should tell another hospital what my preferences are? And the answer is actually maybe. And the simplest way to think about it is that hospitals can collude, right? So if there's two hospitals that maybe have very similar preferences, they might want to collude and strategically together decide how to make their preferences so that the third hospital doesn't steal any of their candidates, right? So actually it's possible that it is beneficial for hospitals to report their preferences to each other and kind of collude in this way. I think it is, unlikely that this happens, and actually would be difficult to find out even beforehand who you might want to collude with. Right? This is another thing that I kind of skimmed over is it's hard for me to know who I want to collude with, because that would mean knowing something about their preferences. So that's a great question. And the answer is maybe you want to tell other hospitals what your plan is. Are there any other questions about matching or about my experience or my research or anything like that? Well, given that I am not seeing anything new in the chat or people shouting it out, I think that that's all I have for you all. Thank you for attending, and thanks to everybody who goes and listens to this recording later. I know that it's probably been a difficult time for you and will continue to be so, but yeah, good luck. Hang in there.
Thank you, Udayan.
Thanks, Miranda.
Bye.
Bye.